Hi everybody, this is Joe/FoozleCC, and today I'm going to be giving an overview on what A Pathfinding is, and specifically I'm going to show an implementation on an undirected graph. I'm going to do it inside of Construct 3 to visualize it, but it's really applicable to any A Pathfinding implementation for an undirected graph. So stick around and let's go ahead and dive on in and see what this is about. Okay, so I fired this up inside the debugger, and the reason I did this is that I have a couple of breakpoints in the code that will allow us to just kind of march through this and visualize what's going on. Our goal is to get from the beginning, where our little green ship is, to this target, which is number 20. And we're going to use A Pathfinding to do this. Now, A Pathfinding can be applied in a number of different ways. In this situation, we're doing it on an undirected graph. And what that means is that we have different nodes and we have edges connecting those nodes. And these numbers represent the weight of that edge for the path that the algorithm is going to use to try to find the most optimal solution. Now, in your games, you might have situations where you don't want to use just a nice grid of rows and columns with all these different obstacles overlaying it. You might need to have specific points that you want to direct your enemies or your player through when they're doing their pathfinding movement. And you might need to be dynamic so that you can keep updating it, maybe if there's an obstacle that emerges. And this is a setup that can handle that type of situation. So let's go ahead and march through and see how this visually works to do A pathfinding. The way it starts is you need to know from the very beginning, who are my neighbors? And in this case, it's 10, 15, 3, and 2. As you can see, connected by the black lines, these are my neighbors. And what I need to do is I need to each time compute the sum of my distance from the start plus a heuristic of the distance to the end. Now, in this scenario, I'm going to use a very simple heuristic, and that's just going to be distance between 2 points. I'm going to use the distance of my x and y versus my x and y of my target as the heuristic value. And I'm going to add that to the sum of my distance from the start point. So in this case, I know that the distance between my start point for 15, for instance, is 398. And then I can estimate, even though I don't know what the path is yet, what my distance is just by using that simple formula. You might come up with a more complicated heuristic, but that's what we're going to use in this setup. So let's go ahead and hit play again. So we've now chosen that we're going to march on to number 15. We decided that 15 had the lowest sum of if you were to add 293 plus the heuristic here, or 137 plus the heuristic here, or 367 plus the heuristic here. Those were all worse options than this 398 plus the heuristic to 20. Now, whenever you see it change to the color red, we're maintaining a list of what we're calling our open vertices. The blue are ones that we haven't touched yet, that we haven't explored yet. And the beauty of A star is it doesn't need to go and explore every single vertice for it to find a path. And that can help save on performance. When it changes to gray, we're calling that closed, in that, you know what, we've already explored all of its neighbors and there's no other neighbors to explore. We're going to close that. So now that we're on 15, we have a new set of neighbors. And now we have to look at each of these that are connected and again go through that same sequence. What is my start distance? And now we know our start distance is 398 because that's how far I am from the start for number 15. And then I have to add on to that for my start distance these values, like 398 plus 283 is the start distance for number 6. I add that to the heuristic between 6 and 20, and I can compute the sum for each of my neighbors and find out what the lowest path is. Now, some of these, you'll notice that I have these rocks that are blocking the path, which makes it, not a viable path. But I also have this debris on the scene graph, these little green, seaweed, whatever you want to call it. And in my setup, I'm using this to allow a scenario where you can add additional weight to that edge. So even though 15 and 14, the distance is much smaller than 570, because I've added all of these debris, it added on the weight that I've assigned to that debris. So you can think about how you can implement that in your game. Maybe you have a car trying to find the most optimal path between point A and point B, and you know what, it can go over the mud, but it's going to be penalized. So that's how you could think about utilizing something like this. So let's go ahead and keep marching. So it decided the next most optimal solution was actually number 3. And that's one of the things that's kind of cool, is that it can actually go back, and it's not necessarily saying that I'm going to go from 15 to 3, but it's saying, hey, you know what? Maybe I should have started with 3. I'm going to go from 3 to number 20, and that's actually the best solution currently. So let's keep going. Now it's going to go to 9, and it's going to say, okay, I got a new set of neighbors. Let's go through and continue to compute it. Now it's going to go to 17. Now it's going to go to 7. Oh, now it's going to go back to 5. So it probably decided, hey, I'm on this path, but then it's like, you know what, guys? Actually, I think 15 to 14 to 5 probably was the better path. So let's keep going. Now it's going on to 19. Now it's going on to 11. And now we're at 20. And it found its path. That was wrong. It wasn't 15 to 14 to 5. It was 3 to 9 to 5 to 19 to 11 to 20. And that's the beauty of A-star pathfinding. And it didn't end up evaluating number 24. If you view it a much larger grid, you can imagine how it would only really touch the neighboring vertices when it's evaluating this, or however you set up your neighbors. So this is how A-star works. You have your starting distance that you know the exact value of, and you have an estimate or a heuristic between your current vertice and the target. And you just keep going through and crunching what is the lowest value to get to my target. All right, now I'm going to go ahead. I'm going to do a quick code through inside of Construct 3 so you can get a visual of how this is being done. I'm going to go through it pretty quick, but I'm going to put the project up on my itch page. So go ahead and download it from there and go through it at your own time. And this also is a good time that if you do enjoy this content, please consider subscribing, giving me a thumbs up down below. It's free for you to do, and it makes a big difference for me. So, okay, let's go ahead and dive into the event sheet. Okay, so in our event sheet, we have two main sections. We have the visual setup, which I won't spend much time on, as well as our pathfinding setup. Now, the visual setup, all it's really doing is, if you go over to the layout real quick, is it's just plopping these vertices down on each of these black dots that I used as a way for me to kind of set up the initial map. You're going to have your own implementation in your own game as to how you're creating these neighbors. I just set this up in a visual way so that we can talk to it in the tutorial. All right, so inside the pathfinding section, this is where it really matters. There's a few things. This is actually just a UI that if we want to make it dynamic, which I didn't really show, let's go ahead and do that right now. So say we want this to be dynamic. You can see that maybe, hey, maybe my target is actually moving around the map. Maybe this is your player and you have a, you know, an enemy trying to follow you. Well, this is a way that you can achieve this, and you can see it's actually updating the graph each time, as well as computing the most optimal path. So this is kind of cool. All right, let's go back. And what you can see that this is doing is, if I do toggle this to dynamic, what it's doing is it's calling this to be run every 0.1 seconds. You can make this driven however you want. It can be event driven, which I recommend, or it can be timer driven, etc. Inside of this section, this is really what's going to trigger us to run the function. Either at the very beginning of the layout it's going to run, or whenever I hit the space bar, or if that timer is running. Once it does that, it's going to do a few things, but the main things it's going to do is it's going to call these two functions. Update vertices, which is kind of rebuild our graph and evaluate, hey, are there any new obstacles? Did you add any things that like mud or debris that are going to increase the weight of one of my edges? It's going to rebuild that graph. And then find path. It's going to use that graph that we just built, and it's going to go from a start position to an end position. So let's go ahead and move on. And then once that's done, it's going to move. This is just simply, you know, ultimately I'm publishing our path into this array, and I'm adding a whole bunch of waypoints to a move to behavior on our player, so it moves along the path. Let's jump into these two functions. Update vertices is the first one that's up. Now, one thing to note is I am going to make use of the line of sight behavior. Specifically, I'm going to use ray casting to determine whether or not I have any obstacles when I'm building out my graph. I'm also going to use it to detect any resistance obstacles. I'm not going to use it to compute what my resistance value is, but just to detect if there are any. And then we'll do something to find out what my total resistance is on that specific edge. There's 4 variables here that I'm maintaining. This neighbor distance is just me deciding, hey, I'm going to dynamically build my graph, and I'm going to say if they're within 450 pixels of each other, then they are neighbors. You can statically define this ahead of time in a data structure, or you can make it dynamic, using distance or some other method. I'm going to be keeping track of how many neighbors there are and having some temporary values for the distance and the resistance weight. Okay, so I'm going to use a JSON object that I've called Pathfinding to keep track of all this information as I march through it to consider what my options are for my path. This is what's going to actually store the vertices and the edges. I'm also going to have two additional arrays. I have my open list and I have my closed list that are both arrays. And this is what's going to keep track of which vertices I've already worked on and which ones are neighbors and are open, or which ones I've already closed out. All right, so let's build our vertice graph. So what we're going to do is we're going to say for each vertex, you might do this in your own way inside your own game, I'm going to add the X and Y of that vertex to my JSON object. Then I'm going to loop through that list of points, and I'm going to evaluate who my neighbors are. So I'm going to loop through each of those points, and then I'm going to also loop through each of the vertices that I have on the map, excluding my own individual vertice. And I'm going to say if the distance is within some threshold, which I've set as 450, I'm going to say, yep, that is a neighbor. Now, before I can do that, what I'm actually going to do is I'm going to say, okay, you should be a neighbor, but let's see if there's any obstacles in the way. So I'm actually going to cast a ray from my current position to that neighbor and say, well, can I reach you without hitting something? And if that's the case, if I don't intersect anything, then yes, you're a neighbor and we're good to go. Now, if I do intersect you, it still may be possible for me to get to you if it's not a solid obstacle, if it's just debris. So what I can then do is say, okay, if I did intersect you, I'm going to drop down this helper sprite that's going to actually just be like a rectangle between the two positions. And I'm going to say, okay, I'm going to put you down here. I'm going to set the width as the distance. I'm going to rotate it so it's this nice little rectangle overlaying it. I can then do this overlapping check and say, if I'm not overlapping any solid obstacles, because we know if that's the case, no path, and I am overlapping any resistance obstacles, I'm going to loop through each of those resistance obstacles that I'm overlaying, and I'm going to add the resistance together so that I can apply that to the weight of the edge. Let's visualize that real quick so we understand what this is doing. So let's set this to dynamic. And you can see here we've got this value is 225. When I put this over it, it goes to 275 because I made each of these worth 50. So 424 goes to 474, goes to 524, and so on and so on. And this allows us to keep dynamically updating these values so that they can have, you know, hey, I've got lots of different debris. I can still go through it, but it's going to be penalized. All right, so let's keep going. Once I've done that, you know, I'm populating certain things to my JSON, my pathfinding JSON. I'm not only have captured the X and Y already, but I'm establishing what my neighbors look like. So let's go ahead and look at what the resulting JSON ends up looking like after I run this once. Okay, so I went ahead and opened up the debugger. I'm going to go over to my pathfinding object. I'm going to take this JSON and copy it so we can read it. Pasting it into here and hitting format, you can see this is what it ends up looking like. I've got each of my vertices listed out here. I have their X and their Y. I have a list of their neighbors that are sitting here. This is just the count, their neighbor number, like 2, 3, 10, and 15. And I have their edge weight, and that is the number that we're seeing visualized on the screen. And we're going to use this for the second function that we're now going to cover. Let's go back to the event sheet. All right, so the second function is find path. If we come on down here, it needs a start number and a target number. So this is going to be unique for your game. In my situation, it's between my player and whatever the target is that I've entered in the game. I'm going to go ahead and zero out my open and closed list as well as my path. And these are the three arrays I'm going to work with here, primarily the open and closed, and at the end I'm going to publish my path. So coming on down here, I've got a number of local variables I'm going to keep track of that's going to help me through this, right? But this is where we're doing that initial kind of walkthrough that we just talked about, right? Where we're going to try to figure out, well, what is my exact starting distance plus what is my heuristic distance to get to my sum? And then I'm going to evaluate that against my other sums to see, hey, is this a good option for me? Remember, I didn't really talk about this, but inside this JSON object, we've got these variables also tied to this vertice. And this is getting constantly updated as we run through this function that we're going to talk to. It's going to calculate the distance from the start. And because we are starting at 1, the distance is 0 for this. What was my heuristic distance? In this case, it was 1619. So the sum of 0 plus 1619 is 1619. And I didn't have a previous vertice. But that's going to be an important variable for us as we go through it, because the way that we string back what the path is we always know what was the previous vertice that led to the most optimal solution. So it's going to keep going through this. For each of our vertices, we're going to go ahead and kind of initialize it by just setting these variables to -1, and that'll just kind of help us make sure that it's back to an initial state, especially if we're dynamically updating. What we're then going to do is, if it's the start number, we have some special conditions. So if you're like the player, or you're the vertice that you're starting at, well, obviously the distance from the start is going to be 0. And I'm going to go ahead and set my temp heuristic distance to the distance between my vertice and my target. And that's going to always be what I do for my heuristic algorithm. And I'm going to go ahead and also compute my sum, and I'm going to add that to the pathfinding JSON. And ultimately, I'm going to push as the very first item on my open list this first initial vertice. And this is where the magic really happens if you're trying to go through this as a pseudocode. We have this while statement. Our current vertex is not equal to our target number. So until we get to the target number, we're going to keep going through this. Now, I do have an exit condition so your game doesn't blow up, where it says, as long as there is that no path is not true. Okay, so continuing on. What we're going to do each time is we're going to set the current vertex object that we're working with to the current vertex that we're going to continuously be setting based off of our lowest sum value that we find. And I'm doing some visualization here by setting it to open so that we can show it as the green. That's open current. Open is the red one. Okay, let's keep going. And then what I'm going to do is I'm going to loop through each of the neighbors, right? So this is what we talked about. We're going to loop through each of the neighbors in the pathfinding JSON object, and we're going to compute a few things. We're going to get, what is my edge weight, right? And what is my start distance? And from there, I'm going to say, okay, by the way, if I'm not on a list yet and you're a neighbor, let's push you onto the open list. Then I'm going to go through all of the items that are not on the closed list, so because we don't need to evaluate those, and I'm going to compute what is my start distance, and that is equal to the start distance of my current vertice plus that edge weight. So we already kind of talked about that, right? But it's always the starting distance of your current vertice you're evaluating plus the edge weight between the two. Then I'm going to do a heuristic distance calculation between the vertice that you're considering, the neighbor, and the target. And from there, I can then do the sum of the start distance plus the heuristic distance. And I'm going to use this temporary sum variable to kind of identify, hey, does this happen to be my lowest value? And if it is, then publish it. So I do an initial check where it says, okay, if it's -1, I know I haven't published it yet. I haven't even evaluated it before because that was what I initialized it to. So automatically just publish it. This is going to be my new, preferred path in this case. I'm going to say, all right, my distance from start is my temp start distance. My heuristic distance is this. My sum is this. And my previous vertex is the current vertex. So I'm going to assign who is my previous vertex in this situation. Otherwise, if there is a value already there, you have to compare your temporary sum to the current value published there and only update the values if yours is better. Once you do that, you can then delete what you just did from the open list, right? After you go through all the neighbors, you delete that from the open list and you push it to the closed list. So now you've considered all the neighbors, it's closed, it's good to go. We have all the information we need. You update it, the open list, and as long as you still have something in your open list at the end of this point in your function, you still have a viable path. If at any point this gets to 0, you need to set this Boolean to true, and this will kick you out of the while statement so you don't get locked in your game. And ultimately what we'll do is we're going to go through each of those items in the open list, and we're going to compare their sums, and we're going to find who is the lowest sum. And whoever that is, that's who we're going to set as the next current vertex or vertice. So whoever was the best option out of that list on the open list, we're going to say, yep, that's the path we're choosing. Let's go that way. And we're going to go through it, and we're going to keep looping in that while loop until I get to my target. So at the end, when I get to the target, I go through here and I loop through and I say, okay, while my current vertex is not equal to my start number, so I'm going to go from the end back to the beginning, and I'm going to look at the previous vertice on each of these. I'm going to publish what my path is. And once I do that, I'm ultimately able to come in here and do this nice visualization. I'm able to say that I found a path, and then my function's done. And I can come back up here to where I called it, and you can see that I'm now going to use that array that's got the path information in it to publish a set of waypoints for my player to move along, and I'm done. And that is A-star pathfinding, everybody, on an undirected graph. So with that said, I want to give a special thank you to all my Patreon supporters. You guys are awesome. Super appreciate it. James Welch, Clone13, McCall, Stevie Conlon, really appreciate it. And for all of you who are considering it, just know that you do get access to all of my premium game assets on my itch page. Feel free to go check them out. A lot of great stuff there. I love partnering with artists and coming up with new asset packs. I update it every month. So give it a look. And with that said, thank you, everybody. Have a nice day.